Hello again, grade sevens. In today's lesson, we're going to look at different types of independent events and how we can organize independent events in different visual fashions. And that's going to involve constructing a table and a tree diagram. And we're going to use these diagrams to identify the number of possible outcomes when you combine two different independent events together. Learning outcome for this lesson is to identify the sample space for a probability experiment involving two independent events. And that's what we're going to start off with by defining what exactly an independent event is. Two events are said to be independent when the outcome of one event has absolutely no effect on the outcome of another one. An example of this would be if you had two objects, you had a coin and you had, for example, like a six-sided dice or six-sided die. Flipping the coin, in which case you can get heads or tails, has no influence on what number on the die you're going to get. If you were to flip heads on the coin, that does not give you a better chance of rolling a 4 on the die. Because flipping the coin doesn't have any effect on rolling a die, we refer to these two events as being independent of one another. It's a bit more complicated when the events are dependent, like if the outcome of one event actually could influence the outcome of another one, but that's not something we're going to worry about at the Math 7 level. To represent these outcomes, we can do it in one of three manners, either with a table, a tree diagram, or a sample space. A sample space is simply a list of all the different possible outcomes for an experiment. If we were to take the example of rolling a six-sided die has six possible outcomes. Either you roll a 1, a 2, a 3, a 4, a 5, or a 6. If I want to represent all these different outcomes in a sample space, what I do is I write down all the possible outcomes, the 1, the 2, the 3, the 4, the 5, and the 6. I put brackets around those outcomes, and I separate them by commas. That's what I would refer to as a sample space. So that's one way in which we can list all the possible outcomes for an experiment. We're going to focus a bit more on the other two, using a table to represent the outcomes of two independent events and also a tree diagram. We'll jump right into an example where we do this. I'm going to flip a loonie. Again, a loonie would have a heads and a tail side to it. And I'm going to roll a four-sided die. If you're trying to visualize what a four-sided die looks like, it kind of has like a pyramid shape to it, except the base of the pyramid, the bottom of the pyramid, has a triangular base to it, as opposed to like a standard pyramid might have like a square or a rectangular base. And if you look at the picture right here, you can actually count the number of sides. Like this bottom face would be like side number 1. This left face on the side here would be number 2. I can kind of just shade them in as well, just to like illustrate them. So this would be number 2. You'd have this right side face to be number 3. Then you also have the front face here, which I'll just illustrate with a different color. So the front face would be this entire face. And this entire face would be the fourth possible side. Okay, so what I want to do is I want to use a table to express all possible outcomes in the experiment. And I also want to do the same thing with a tree diagram. So we'll use both of these ways to visually represent the outcomes. All right, so I'll start with the table. So what I'm going to do is I'm going to begin by identifying, I'm going to take one of the objects. I'm going to take the loonie. So I'll write down the word loonie here. And for a loonie, make a little table. Let's draw some grid lines, I suppose. For a loonie, you have two possible outcomes. Either you can flip heads or you can flip tails, one or the other. Now, up here, I'm going to write down die. And for the die, it's a four-sided die. You have four possible outcomes. You either have a 1, you have a 2, you have a 3, or you have a 4. Okay, those are my 4 possible outcomes. Now, what I'm going to do is I'm going to combine the rows of the table. So the rows of the table go horizontally across along with the columns that go vertically. And you can just combine the different letters and numbers together. So one possibility is you could flip heads and you could get the number 1 on the die. Another possibility is you could flip heads and you could get the number 2 on the die. A third possibility is you could flip heads and get a 3 on the die. So we write H and then 1. So that's showing the two different independent events, the flipping of the heads and the number you get on the die. You could also flip heads and get the number 4. You could flip tails and get the number 1. You could flip tails and get the number 2, tails and the number 3, and then tails and the number 4. That's a table. If you wanted to make the table a little bit more organized, you could draw some more grid lines. I mean, this is not totally necessary, but you could put a grid line like here. You could put a grid line there, another grid line here, and do another one. Then you have the grid line separating all the different possible outcomes, but that's not totally necessary. Just kind of like a rough table just to sketch here. Nothing too fancy at this point. Okay, that's a table. Now, we're also going to construct something called a tree diagram to show all the possible outcomes. So the way tree diagram works is we're going to pick one outcome to start off with. Typically the outcome, I'm going to pick one object to start off with. Typically I like to pick the object that has the fewer number of outcomes. So that's going to be the loonie. So I'll write down loonie here. And for the loonie, there's 2 possible outcomes. Either you can have heads or you can have tails. Okay, one of these 2 things. Now, I'm going to write down the second object, which is the die. And here's why it's called a tree diagram. We're going to represent the different outcomes for the first object as being the trunks of the tree. And then the trunks of the tree are going to branch into the different outcomes of the second object. So for example, here, we could have heads that branches into a number 1, because you could get heads and the number 1 on the die. You could get a heads and then a number 2. You could get a heads and a number 3. You could get heads and you could get number 4. Same thing for the tails. So I have the tails would be the trunk of the tree, and then this branches off into the outcomes for the second object. So that'd be tails and then 1. This would be tails and then 2, tails and then 3, and then tails and 4. That's a tree diagram. You have your trunks on the left-hand side, and that branches into the different outcomes for the second object on the right-hand side. I personally find it a little bit faster to do a tree diagram compared to a table, but nonetheless, it's important that we can still represent them both the table and a tree diagram. It also says write a sample space for the combination of events. So a sample space, again, is where we write down every possible outcome. We put them in brackets and we separate them with commas. So what this would look like is you would have heads and 1 is one possible outcome. You have heads and 2, which is 2 possible, the second outcome. Heads and then 3, and then heads and then 4. And we could also have tails and 1, tails and 2, tails and 3, and then tails and 4. Those are all, that's my sample space. So all the different possible outcomes of the 2 independent events, you put them in brackets, you separate them with commas. D, I want to identify how many possible outcomes there are if you combine these 2 independent events together. For sample spaces, it's really easy to do. You just count the number of outcomes you have in brackets. So that'd be 1, 2, 3, 4, 5, 6, 7, 8. So the number of possible outcomes, which I'll abbreviate with PO, would be equal to 8. Now, if I go back to the previous diagrams, we can also count the number of outcomes. For a table, it's the number of these little entries where you combine the 2 outcomes together. So you have like heads and 1, that's 1 outcome. this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, and this is 8. For a tree diagram, to count the total number of possible outcomes, you just need to count the number of branches you have on the tree. So you have 1, 2, 3, 4, 5, 6, 7, 8. I mean, you combine the heads with the numbers I've circled here and the tails of the numbers I've circled, but the number of branches does tell you how many possible outcomes there are going to be. Okay, so you have 8 possible outcomes. Okay, let's make this a little bit more difficult. I've said here, suppose heads is assigned a numerical value of 1 and tails is assigned a numerical value of 2. Normally, you would not do this. I'm just trying to make the problem a little bit more complicated. Now it says, in an extra column in the tree diagram, determine the sums of the 2 outcomes along each branch. Okay, so let's go back to this previous tree diagram. And what we're going to do is we're going to assign a value to heads and tails. We're only going to do this if the problem actually tells me to do it. Most of the time, it will not do that, okay? So we're going to assign the number 1 to heads and the number 2 to tails, okay? That's because it just tells me to do that. Assign heads 1 and then tails with 2. Now, it then asks me to make a third column. So we'll do this in red. And we're going to call this third column sum. What I'm going to do here is I'm going to find the sum of the trunk and the branch. Okay, so if you follow this one, heads, if it has the trunk has a value of 1, you combine it with this branch of 1, the sum means add together, so 1 plus 1 would just be 2. If you go along the second branch, the trunk, which has a value of 1, combined with this branch, 2, 1 plus 2 would be 3. Then you go 1 plus 3 would be 4. Then you go 1 plus 4 would be 5. Tails, the problem has just told me to assign a value of 2 to it. So 2 plus 1 would be 3. And then 2 plus 2 would be 4. 2 plus 3 would be 5. And then 2 plus 4 would be 6. So I've created a third column where I just identify what the sum of the value attached to the trunk of the tree is, along with the value attached to the branch. Okay, I got the sum of these 2 different things put together. Now, what F wants me to do is it wants me to identify what are the sums that are the most common. So that just means the sums that tend to pop up the most. So if we go back to my picture here, let's actually see which ones appear the most. So let's just identify this in red. Okay, a 2 only appears a single time. A 3 appears here, and it also appears right there. Okay, so a 3 appears twice. A 4 appears here, and it also appears right there. A 5 appears here, and it also appears here. A 6 only appears a single time. So the most common sums are the ones that occur the most. So a sum of 3 occurs twice, a sum of 4 occurs twice, and a sum of 5 occurs twice. So I'm going to identify those as being my most common sums. So most common sums are 3, 4, and 5 in this particular situation. So, like I said, just a E and F are just a small extension to make the problem a little more difficult. Normally, though, you do not attach a value to like heads or tails. Okay, I just did it just for the context of this problem. Most common sums is something to consider when you're like playing like a game where you have two different dice. If you had like 2 different 6-sided die and you're trying to think about like what the different most possible outcomes are, that might be like a way to like consider how to like strategize a particular game. All right, so that's it for the end of this lesson, and you can complete on page 169 numbers 4, 5, 6, and 8. I did make a couple of notes here. I said when you set up the table, a tree diagram, or a sample space, use abbreviations for the words. I think there's one example where like you're using like there's like the word tire that's cut out on a piece of paper or rainbow that's cut out on a piece of paper. instead of writing those words fully out, I would just abbreviate them, like T for tiger, R for rainbow, just to make the setup of the tree diagram, sample space, or table a little bit faster. The other thing too is that when you are constructing a tree diagram, you cannot have the branches actually overlap. So what I would not want to see is, like, for example, if you had like heads and then you had like 1, 2, 3, 4. Okay, and you kind of like drew some like lines that went out like this. And then you put down tails here, and you're like, oh, I don't want to draw 1, 2, 3, and 4 again. So I'm just going to do this. I'm going to simply just make the tails go up here to the 2, to the 3, to the 4. Okay, that's really messy. I can see like the red lines and the purple lines crossing each other. That's something that's not allowed in a tree diagram. You would have to draw the outcomes for the die a second time. No crossing over, no overlap between the different branches. That's it for this lesson, and I'll talk to you in the next one.